This example is called a random walk on a network. So let's see how it works. I'm gonna first define a network, what that is, and then I'll give you an example, and then we'll run some calculations with Markov chains and stationary distributions. So, a network is a countable set of vertices, right? So just think of a collection of numbers that are labeling these things called vertices. Sometimes they're called nodes. But if you want an example right away, that one is right here. This is a network, and the nodes are those dots that are labeled 1, 2, 3, 4. So my set of vertices in that example is just the set 1, 2, 3, and 4. I mentioned countable there because it can in fact be infinite. So I could have a set of vertices that's maybe the whole all the natural numbers, but it cannot be the real numbers because it has to be countable. We also need this thing called the weight function, and the weight function takes two elements of the vertices, so it takes two vertices and spits out a real number that's non-negative from 0 to infinity, not including infinity. The other constraint we have is that this weight function is going to be symmetric, meaning that for two vertices xy, wxy is equal to wyx. And so what I've done in this example here is that I put the value of the weight function on what are called edges. So the way to read this is that for any between any pair of vertices, there is going to be a value that this weight function provides. So for example, for vertices 2 and 3, w23 is 2, and I wrote all of them out on the left there, so you can kind of check right against your intuition here, right? w12 is equal to 1, right? And it should correspond to the labels on these things called edges, and those are the lines connecting the vertices. That's what an edge is by definition. That's the terminology that comes out of graph theory. So in next, why there are some edges missing, like why aren't there any lines connecting 3 and 4? Well, essentially what we mean here is that the weight function assigns a 0 weight to that connection, right? So there's no connection between 3 and 4, right? W34 is 0, and so is W43, and that's by symmetry, right? So these are networks, and it's popular in analysis of all sorts of graphs, including the Facebook graph and all other sorts of social networks. And network theory and graph theory are useful in many ways. But for now, we're going to focus on Markov chains on these networks, or random walks on networks. So what I want to define is this function lambda, which is a sum of the weights over the second coordinate, right? So lambda x for any vertex x is defined as the sum of the wxy over the second coordinate, which is here is y. And they're going to be finite. So it's possible that this sum doesn't converge, right? It's possible that it hits infinity, and here I'm saying let's just assume that these weights, the wxy's, are such that there's convergence in that sum. And obviously for any v that's finite, right, a finite number of vertices, like here it's 4, obviously that's going to be a well-defined and finite sum. So just to run through what lambda looks like, you can kind of check against that example. Hopefully I got all those right. All I'm doing is I'm going to every vertex, like I go to vertex 1, and I go across all the edges, and I sum up the numbers that are listed on the edges, right, the weights of the edges. And so lambda 1 is equal to, right, I look at the edge going from 1 to 2, and I pick up that one, and then I also pick up the one from 1 to 4. That makes 2. Why is lambda 2 4? Well, lambda 2 is connected to 1 and 4 with weights 1. That makes 2. And then there's another 2 coming from the edge to vertex 3, so that makes 4. Lambda 3 is 2 because its only edge goes to 2 with weight 2, and lambda 4, so vertex 4 has a lambda function of 2 with 2 edges going to vertices 1 and 2, both of weight 1, so they add to 2. Okay, so I'm glad I picked a small example. Alright, so what's next? I lost my train of thought here for a sec. We're going to define now a random walk on this network, and I'm going to claim that, that it's given by the following set of one-step transition probabilities. So just because I say it doesn't mean that, that these are actually one-step transition probabilities, and you can try to, as an exercise, think through why would these be one-step transition probabilities? Namely, why do these numbers that I've defined, and I've defined them over the vertices in V, right? X, Y are vertices in V, and so the state space for this chain that I'm trying to construct is also going to be V, right? How do we know that these are actual one-step transition probabilities? They have to be between 0 and 1, and they have to sum to 1 when summing up over the second coordinate, right? The chain has to go from X somewhere, and I'm going to sum over all possible values of Y, and that thing better be 1, right? And that's an easy thing, simple exercise to verify, and I'll leave it to you. So now, once this thing is defined, like what happens? What happens is all of a sudden this Markov chain kind of comes to life, right? And it takes values on the vertex set. And so you can kind of picture this Markov chain moving on that network there, right? It's just moving around. And now the next question is, how do we get some intuition for how it's moving around? Well, you can look at what it's doing. Its probability of going from a vertex X to Y depends on the weight on the edge that connects it to its possible sort of candidate, right, step, right? So it's probably better to look at it as an example. So let's start at vertex 3. So I'm going to start my random walk on vertex 3, and I'm going to ask, where's it going to go? It's not going to go to 1 or 4 because W3, 4, and 3, 1 are 0 because those edges are not drawn in, which implies that those weights are 0. The only vertex it could possibly go to is actually 2. It has a weight of 2, and the lambda, if you compute it out, or actually we don't need to compute it out, it's right there, the lambda of 3 is 2, and so you have a probability 1 of making a step from 3 to 2. So starting at 3, the Markov chain always moves to state 2, or rather vertex number 2. And now there are kind of quite a few decisions to make. You can go to 1, you can go to 4, you can go back to 3. And you can try to think through what the probabilities of all these moves are. So for example, 2 to 1, stepping from vertex 2 to 1 is going to have probability 1 over lambda 2, so that's 1/4. Stepping from 2 to 4 is going to have a probability of 1 over 4 again, right? 1 over lambda 2. And then stepping to 3 is going to have a probability of 2 over 4, so 1/2. So this Markov chain starts at 3, definitely goes to 2, and then there's a 1/4 probability it steps to 1, 1/4 probability steps to 2, and a 1/2 probability that it ends up at 3. And then just keep running this thing, right? Just keeps walking around over and over, right, for forever. And of course the question I'm going to ask here is, well, what's the stationary distribution, right? Where do we expect to see this chain in a long time? You can maybe even kind of guess right away if you have a good enough intuition, and this is what you should be trying to kind of think through with every problem. What do I think is going to happen, right? Is it more likely to spend more time in vertex 2, right? Or is it more likely to spend more time in vertex 4 in the long run, right? So in the long run, it's going to be visiting all these states. But, what's the probability that it's going to be, that we're going to find it in state 1 after a long time? What's the probability that we're going to find it in state 2, right, in vertex 2 after a long time? So you can try to guess it. It seems to me, at least kind of intuitively, that this vertex 2 seems to be that's going to get a lot of visits, right? It's more likely to find it there. It seems to me, just because of its kind of central location on this network. And kind of from 3 you always go there, from 4 you can go there, you can get to it from every other vertex. And so my guess would be that the probability that it's at 2 is going to be larger than the probability of the others. But well, let's see, we'll work it out. So that's essentially what we're trying to work out, right? Instead of guessing, we're going to try to compute the probability that this chain, this random walk on the network, is going to be found in either state 3 or vertex 2 or vertex 4 or vertex 1 after a long time. So I'm going to do it the hard way, which is the global balance equations. There's an easier way, which we'll do, and you may guess it has to do with local balance. But let's discuss the global balance equations, which are going to be quite messy. It's still good practice to write them out. So how do I write the global balance equation for mu1? I have to look for all states that lead to 1, and that's going to be 2 and 4. And I go from state 2 to 1 with probability 1/4, and I go from state 4 to state 1 with probability 1/2. And I'm going to say state and vertex sort of interchangeably because they're the same thing. So now that's one equation, my first global balance equation for vertex 1. Now let's do vertex 2. How do we get to vertex 2? We can go from 1, we can go to it from every other vertex, right? From 1 we get to it with probability 1/2. From 4 we get to it with probability 1/2, and from 3 we already saw that we always step to it, so there's a times 1 here. All right, and then you keep going, and maybe you can check me on the others, right? 3 is easy, right? The only way to get to 3 is from 2 with probability 1/2, or 2 over 4, and then from 4 you can get to 4 you can get from 2 and 1. And so ideally you're kind of already getting good at writing this up and kind of crunching all these numbers. And here we can pause a little bit and kind of say, well, so what's mu? And one good thing is we get to pick one value of mu for free, right? And so here you can make a choice. One could try to I would pick either a mu2 or a mu3, because as soon as you pick one of those you get the other for free. And then all you have to do is just solve the remaining 2 equations and 2 unknowns. It's messy, but you can do it. So what's the alternative, right? That's local balance right here. And you should get good at writing these equations as well, and they're particularly easy here. First of all, I have to consider kind of pairs of vertices, and there's no point considering any pair that doesn't have an edge between them. So I'm going to make 4 equations, right? Because there are 4 edges, right? Every edge is a pair that I care about. Whenever there is no edge, there is no probability of going from one from the other. So the local balance equations hold there no matter what. All right, I'm going to pick the pair 1, 2, right? There's a probability of 1/2 of going from 1 to 2. That's this 1/2. There's a probability of 1/4 of going from 2 to 1. So that's local balance equation number 1. And now I pick the edge 2, 3, right? You go with probability 1 back to 2. You go with probability 1/2 from 2 to 3. And then so on. Check me on this. I think I kind of got those. Hopefully I got those right. They're pretty intuitive. So now, obviously much easier to solve this thing. We still get, by the way, 1 choice for free, and it will be much easier to solve this than it is to solve that. So let's write out what we get. So we get 1 for free, so I might as well pick this one, and I'm going to make the choice 2 that I'll explain later. But the point is I do get to pick one, and I get to pick it to be anything. Doesn't have to be 1 was my choice before, right? We picked mu0 is equal to 1 for the renewal chain and the birth and death chain. Here I'm going to pick mu of 1 is equal to 2. So if that's the case, right, then what does that give me for mu2? Well, you know, this is going to be 1 times 4. It gives me a 4. What do I get for mu3? I can use this equation. It's just mu2 divided by 2. 4 divided by 2 is 2. And what's mu4? Well, I can go maybe with this one. The 1/2s cancel out, and it's the same thing then as mu1, which is 2. What you should have noticed, or should be about to notice, or is that mu is equal to lambda. Right, so the values for lambda now match the values for mu, and in fact it turns out that a lambda is going to be the stationary measure, not quite the stationary distribution, for any random walk on a network like this, as long as the lambdas are, you know, finite. So that's something that you're going to explore more in homework too, so I won't mention anything additional. But you know, the question is, how do we finally get the stationary distribution? What's pi for vertices 1, 2, 3, 4? Well, it's just a normalized version, right? It's basically those numbers, provided that they sum up to 1, right? So we just have to sum them up and divide each by that sum. So the way I count it is this: the sum looks to be 10, right? 6 plus 4, 10. So that means pi of 1 is equal to 2 over 10. So let me write them up here. Pi of 1 is equal to 0.2. Pi of 2 is equal to 0.4. Pi of 3 is equal to 0.2. And pi of 4 is equal to 0.2 again. Right, and that sums to 1, and it's you know, exactly like lambda, which is exactly like the stationary measure, just normalized. So there's that. Random walks on networks, and you'll get to play around with them some more in homework too. We're actually going to end up showing that every reversible Markov chain is a random walk on a network, and every random walk on a network is a reversible Markov chain. So this local balance condition applies only to Markov chains that can be represented in this way, you know, represented as random walks on networks.